Alright, trig functions. Even though these things can look a little bit gnarly, especially when you get down here, we're basically looking at the same set of integration formulas we've been using with x. So we just replace the u's with du's. But you can see that they're all the same. Secant squared is still going to integrate to tangent. You'll notice that wherever you have an u, you have a u on the right. So that means if you're integrating a secant squared of 5x, you have a tangent of 5x on the right. That's what this u means. But of course, we're going to end up generating some halves and some whatevers out front. Just like in the power rule, when our du did not match our u, so we had to like conjure up a 2 or a 5 or whatever, which meant we had to put a 1/2 or a 1/5 or whatever out front. Same is going to happen a lot on these trig function integrals. So let's take a look. Now, as usual, we're going to want to match our u and our du. So the first thing we'll do is say, you know what? This is a sine. And of course, the sine formula has a u in it behind the sine. So that means my u in this case is 5x. Now, du would just be the derivative of 5x, which would be 5 dx. So the question is, do I have a 5 dx? No, I don't. I just have a dx, which means I need a 5 there and a 1/5 there. But aside from that, it's going to be 1/5. If we want to be all technical and stuff, so one thing you would just be like, oh, negative 1/5 cosine of the same stuff. That would just be the way I do it, doing it Chris's way, if you watch the second video in this chapter. The other way to do it is if you got the more mathy teacher who makes you write everything out, you could rewrite it at this point as 1/5, and then of course this is just sine of u, and the 5 dx is just du. So we just rewrote it in u form. So it's going to be 1/5 times the integral of sine, which is negative cosine u. The integral of sine u is negative cosine u, plus c. And then as a last step, we'll rewrite that by getting rid of the u and putting it in x terms again. And of course, that would be cosine of our u, which is 5x. So you get the same thing either way. It's just a question of whether you do this intermediate step of putting things in terms of u and actually doing the integral when things are in terms of u instead of in terms of x. Similar thing's going to happen here. Since we're integrating a cosine, you might be a little nervous that there's an x out front, but hey, that's never stopped us before. A lot of times that turns out to be part of our du. So, figure, first thing I always try is if I see a cosine, I just figure it's probably the cosine rule. So let's try setting cosine u is equal to just x squared, because it's what the cosine is of. It's going to be our u. So if u equals x squared, our du equals 2x dx. All right, so do I have that? Not quite. I've got an x and I've got a dx, but let me rewrite this with that x more where it belongs. Cosine of x squared times x dx. And this is where you can see that I'm really close. I just need a 2 right here, and therefore I have to put a 1/2 out front. So at this point, I've got a 1/2 integral of doing it the mathy way. This would be the cosine of u times du, which is going to be 1/2 sine of u plus c. And this last step, I will stick in, sub back in, instead of u, I'll put in my x squared again. So 1/2 sine of x squared plus c. So you can see this is going to get a little bit predictable. If you just have a 5x or 6x or some number sort of in there, then you'll just end up with 1 over that number out front. And some teachers actually teach this as, oh, the integral of any number times a is just 1 over that number times the cosine or whatever. Anyway, you'll see these get pretty repetitive. Where they get tricky is when you get into some weirder stuff. Just like with the fraction exponents and the rational expressions, it wasn't super obvious sometimes what was your u and what's your du. That can happen here as well. So if we're looking at this, it's a secant squared, which might seem a little intimidating, our power rule at first, except remember secant squared integrates to tangent, because derivative of tangent is secant squared. So there's actually just the secant formula. And our u is pi minus x, which would mean our du is just negative dx. So this is actually ready to go. I just need a -1 in front of here, which means I need a -1 outside to cancel out the -1 I just randomly put in. So integral of, so there's really the integral, and I'll just rewrite it as in u form, since some teachers like that. So negative secant squared of u times du, because negative dx is just our du. All right, so that's just going to integrate to negative tangent. Keep our negative out front, and then secant squared goes to tangent of u plus c, last step, replace u with our pi minus x plus c. Now, if you don't have a rigorous teacher, the Chris way would have been just to say, you know what, secant squared integrates the tangent of the same stuff. So once I got this done with this step and realized I needed a -1, I would have put the -1 and -1 out front, and then I just would have gone straight to, oh, integral secant squared is tangent of the same stuff. So I just would have been tangent of the same stuff, and I would have skipped this whole pair of u steps right here. Just depends on your teacher. Not a bad idea to be able to do it both ways. Usually if you do something 2 different ways, it's a great way to get it right. Or get really confused if the 2 ways don't agree and you're not sure which one's right, but hey. Alright, this one's going to go similarly. Again, secant times tangent seems really, I don't want to say scary, but it looks pretty messy until you realize that, wait a minute, secant times tangent is just the derivative of secant. Therefore, the integral of secant tangent is just secant. So this, and then this x might just be part of our du, because if we're doing that secant tangent thing, now you'll notice these are both pi x squareds. They have to be. If you're going to integrate something like this, they've got to be the same arguments. You got to have pi x squared, 5x, whatever. They've got to match. But once you got that, you got u equals pi x squared. So du equals 2 pi x dx. And of course, I've got the x. So what I need is a 2 pi. So now I've got a 2 pi and an x and a dx. I just need a 2 pi there, which means I need a 1 over 2 pi out front. So it's going to be 1 over 2 pi times the integral, let's do it the mathy way, shall we, of secant u tan u du. So now when you actually do the integral, you got 1 over 2 pi, because that's what was out front, and then secant tangent integrates to secant of u plus c. It's quite a bit less complicated. Equals 1 over 2 pi times secant. Now we're just going to replace u with what u is, which is pi x squared. Alright, turned out to not be that bad. Just remember when stuff's multiplied together, you just want to keep those in the back of your mind. Secant tangent, cosecant, cotangent. It seems like with integrals, they usually just use the main 3, sine, cosine, tangent, and secant. They don't usually do cosecant or cotangent, but you know, if you have a mean teacher, and especially if you're an AP at a hard school, decent chance you'll see those as well. Alright, tougher to spot? What's up with this thing? This is one of those ones where you just got to sit back and wonder, what's my u and what's my du? The most obvious rule to use here is cosine, because if I made x squared my u, then what's that? Just like, I don't know, a power rule or something? That cosine just wouldn't need to be there. So this is probably a cosine problem. And just on a flyer, let's just try setting u equal to whatever the cosines of, because that's what I have to do anyway. So that'll just be x to the minus 1 is a rewriting of 1 over x. And what would my du be? Well, so it'd be negative 1, so it'd be negative x to the minus 2. Oh, hey, look at that. That's what this is. So I've already got the x squared, so it turns out that thing that looked so bad was actually a really well disguised du, or a tricky looking one. So if all I need for my du is a negative 1 over x squared times dx, I've already got the dx and the x squared, I just don't have this negative sign, which means I just need to put a negative 1 here and a negative 1 out front to conjure that negative sign. Now I'm all set. So this is negative times the integral of cosine of u du. Excellent. Integral of cosine is just sine, so this is going to be negative sine. Just keep that negative sign out front where it was. Negative sine of u plus c, which is going to be negative sine of 1 over x plus c. Alright, not too shabby. So you can see that x squared downstairs is the derivative, or can be the derivative of 1 over x. Kind of random. Anytime you're dealing with negative powers, the derivatives get into big exponents in the denominator pretty quickly. Alright, this next one, really hard to spot how to do this. There's actually a big trick, and it's one of the tricks you learned in trig proofs. So it turns out we're going to do some algebra on this using trig identities. Basically, this thing will not integrate now because I can't use the sin x rules on it, because sin x is with that 1, it's in the denominator, so it's not just like integrating sine. It's 1 over a bunch of stuff that happens to have a sign in it. My u couldn't be 1 minus sine x, because then my du would have a cosine in it, and I don't have a cosine. So what I'm going to do is I'm going to do some clever algebra. I'm going to multiply this thing by 1 plus sine x, top and bottom. And that's, that's the kind of thing you do just to change the denominators of fractions and stuff. But here's the big trick. When you have 1 minus sine x, you multiply by 1 plus sine x. The reason we see that all the time in trig proofs and stuff is it gives you a 1 minus sine squared downstairs. Which, if you remember your trig proofs, is good because that's cosine squared. So now we've got a 1 plus sine x all over cosine squared. Oops. So that might not look like that great to you, except check this out. Now instead of having two terms downstairs and only one upstairs, which is not algebraically anything I can do something with, this is now sort of two separate fractions. So I can break this up into two fractions. I can break it up into 1 over cosine squared x dx plus the integral of sine over cosine squared dx. Why is that so great? You're probably still looking at me like, I don't see what we've gained. Well, this is the integral of secant squared x, which is just going to be tangent. And then the integral of this other one is actually an interesting power rule. It's cosine -2 of x, so cosine to the -2 power, sine x dx. All right, you're still probably looking at me like, why is that so wonderful? Well, integral of secant squared is just tan x, so that worked out pretty great. But then this other thing, we got cosine to the -2 power times sine x. That might seem kind of bad, except sine is the derivative of cosine. So you can actually use power rule on this cosine. If you have if you set u equals cosine x, then your du is just negative sine x. And I've got that, except I need a -1. So I'll just put a -1 out front. So that's really subtracting, and then the integral of cosine, it's integral of u to the -2 du. Because cosine to -2, and then sine x is just part of the du situation. So at this point, still have 10x, and then minus the integral of u to the -2 is u to the -1 over -1, which is really just going to change the sign. So that's just tan x plus u to the -1 is going to be 1 over u, which was cosine x, which is actually just secant. So we can reduce this even more. Tan x plus secant x, and of course the ubiquitous plus c. That was pretty crazy. So you can see the trick was just recognizing, and there's no way you would have come up with this unless you had done a lot of these and you've seen trig proofs recently and stuff. But basically, anytime you have a 1 plus sign or 1 minus sign, if you multiply by the conjugate, you'll end up with this 1 minus sine squared situation that turns into cosine squared. So you want to remember your trig identities. All right, let's take a look at some more power rule examples involving trig functions. Now, since I have a tan to the 7th, that 7 is just screaming out, hey, use power rule on me. So I don't know. Let's see what happens. If I want to use power rule on tan of 3x, that would mean that u equals the tangent of 3x, right? Du, therefore, is secant squared 3x. And then remember, we're doing the chain rule, because the derivative of tangent of 3x is secant squared 3x times 3. So basically, the du, just to rearrange that, is 3 secant squared 3x. So you see how the secant squared actually wasn't a big mess. It was really great for us, because that's our du. The only thing I'm missing at this point is a 3, which means I need a 1/3 out front. So now I've got my 3 and my secant squared, 3 and secant squared, all set. So this is 1/3 tangent to the 7th, so that's just u to the 7th. And then all this junk with secant squared is my du. So that's what it reduced to. So that's 1/3 times u to the 8th over 8 plus c. So that's 1/24 tangent to the 8th power of 3x. Pretty wild. All right, what's going to happen with this one? Well, gosh, this looks an awful lot like the previous problem, right? Except this time, instead of secant squared, which is great because it's the derivative of tangent, I've got a secant to the 3rd power. Not so bueno. Well, it turns out this is a tricky one. You just wouldn't be able to spot this unless you'd seen something like this before. But now that I'm going to show it to you, you'll be able to recognize it next time you see it. Remember that the derivative of tangent is secant squared, and that's what helped us last time. But there's also a secant tangent in problems that are derivative of secant. So if we made our u secant of 3x, then our du would equal secant 3x tangent 3x, and then because the chain rule I have to multiply by the derivative of 3x, 3. So you'll notice that a secant times a tangent could be part of our du. So what we're going to do is just break this up. We're going to say, well, hey, if our u is secant 3x, I'll put that first. And what's the power of secant I've got? Not sure yet, but I do need a 3 secant tangent as part of my du. And since I'm putting a third in, because I don't have this 3 yet, that's nowhere to be found. So I'm going to put in a 3 right now, and that means I have to put a 1/3 out front. But 3 secant 3x tangent 3x is just my u. So so how many secants do I have left? I use the tangent right here, and I've got a total of 3 secants. And I've already used 1 as part of my du, which means I only have 2 left. So does that make sense? I basically took this secant cubed and broke it up into a secant and a secant squared. I use the secant squared as part, like basically my power rule thing, and then I use one of the secants as part of my du. But now that that's done, I've just simply got a 1/3, and then the integral, I won't do this one the mathy way, I'll just do it flat out. Secant squared, you just raise the exponent by 1, so that's secant cubed 3x, and you divide by the new power, which is 3. So that is going to give us 1/9 secant cubed of 3x. So pretty crazy. We started with a secant cubed with a tangent on it, and ended up with a secant cubed without the tangent, and then we got a 1/9 instead. So pretty wild. Looks like the two big tricks there were we had to remember the chain rule, so I needed a 3 here, which led to a 1/3 out front. And of course you always divide by your new power, so that's where the 1/9 came from. And plus c, why didn't you remind me? Gotta have a plus c on that puppy if we want full credit. Alright, so this one's kind of wild. I've just written the same problem twice because we're going to do it twice. Just want to show you it doesn't matter if you find the exact right way to do it at first, because on these trig problems there's often 2 different ways to do things. And we can actually use each of the 2 methods we used on the previous page for 2 different problems we can use for the same problem. So on this first time, I'm going to look at it and remember, you know what? The derivative of tangent is secant squared. That can't be a coincidence. So let's make our u tangent of 3x, and that way our du will equal secant squared of 3x dx, and of course chain rule means I have to put a 3 in here as well. So I've pretty much got that already. I just need a 3 here, and then of course a 1/3, and now we're all set up. So this will integrate to 1/3, and then I'm going to actually write this the mathy way so you'll see. When you look at tangent of 3x, and that 3 kind of looks like a power, but really it's kind of in here. Anyway, let's put it over here. This tan x, doesn't have a power on it. So when you're looking at that, you're probably not thinking to yourself, hey, I could do the power rule. But if you rewrite this in u form, tangent 3x is just u, and then all this other stuff is du. So if you look at it that way, doesn't this look pretty obviously like it's got to be a power rule? I mean, it's just u. Integral of u is u squared over 2. So you can see that even though the exponent of the original tangent was only 1, that doesn't stop you from doing a power rule on it anyway. So we get 1/6, 3 times 2 is 6, and then u squared, so that'll just be tan squared plus c. Alright, pretty sweet. That's what we get doing it that way. Let's try it the other way. Now what is the other way? The other way is if I take the secant squared and realize, you know what, if my u was secant of 3x, then my du would equal secant of 3x, tangent of 3x, and of course once again I need a 3 out front because of the chain rule. And I have that. I've got a secant and a tangent, but I also have another secant. So what I'll do is I'll rewrite this as secant of 3x, and then I'll multiply that by secant sorry, secant of 3x tan 3x dx. So you can see now I still have two secants, so that's the same as secant squared, and I have a tangent still, so I didn't get rid of anything. And now all I need is a 3 and a 1/3. Now my u is secant 3x, right? So if I rewrite this in u form, that's 1/3 the integral of u, because this is u, and then all this stuff is du. So you see I once again get the exact same formula, 1/3 integral of u du. So it was 1/3 u squared over 2 plus c, which is going to equal 1/6 u squared plus c, which equals 1/6. And if I sub back in my u, I got secant squared 3x. Alright, so now at this point, you should be thinking to yourself, geez, Chris, you told me that you were going to get the same answer, that you could work the problem two different ways. And yet you got two different answers. You got 1/6 tangent squared and 1/6 secant squared. How the heck does that add up? Well, it turns out these are actually slightly pretty similar answers. Because remember the plus c? Remember how a plus c can be any number? Like we don't know what number it is. It turns out that these two functions are actually very closely related. Because there's a trig identity which says that 1 plus tangent squared equals secant squared. So basically secant squared and tangent squared are equal to each other with a vertical drift of 1. So all you'd have to do is if one of these c's was 1 bigger than the other, all of a sudden these are your exact same curve. And just to show what these look like, you know, if you graph this on your calculator, oops. If you graph 1/6 secant squared and 1/6 tangent squared, and you'll need to shrink your window down probably to see this, but one of them basically goes like this and bounces along like that, and then the other one is going to bounce along like this. It's just the same function, just under the other one. So, you know what? That's not what these look like. I just did sine squared and cosine squared. Point is, they're same graph. They're just above each other. And now that we bring it up, I'd be interested if you type this into your calculator, because it'll happen more than once in calculus. You come up against a problem, you can integrate two different ways and get two slightly different answers, but get the same thing. All right, so here's another one. And this is actually the graph I was thinking of that I just drew for you a second ago. We can do this one two different ways. So we could say, hey, you know what? The u equals sine x, and therefore the du would be cosine x dx. That's just derivative of sine x. And look at that, I've already got it. So this is the integral of u times du, because there's my du, and there's my u. So that's going to be u squared over 2, which is sine squared over 2 plus c. Or I could integrate it as, well, this was method number 1. Method number 2 is like, let's just switch them. Let's say u equals cosine x, and du equals negative sine x. So I'm going to take the derivative of cosine, it's negative sine x. So now I'll integrate it. So integral of u. Now I have a sine x, I don't have a negative. So for this one I'm actually going to need to, let's get rid of the u for a second here. So let's rewrite this. My u is cosine x. I got a sine x dx. I just switched the order cosine and sine. But I need a negative 1 to make this du work out, which means I need negative 1 out front to make up for the negative 1 I just added. So that is going to integrate to negative cosine squared over 2 plus c. So once again, just like the last problem, you'll notice that I've got two really similar looking functions that do not appear to be equal. So it looks like I kind of did something wrong because I have two different looking things. But this is the one I was thinking of that I graphed. I've graphed before, where sine is basically just a wiggle, a squiggle that goes across the page, and so is cosine. But when we throw this negative sign in front of it, that makes it below the x-axis, because sine squared is always positive. So instead of doing the usual sine thing where it goes above and below the x-axis, when you do sine squared, you get something that's more like this, where it bounces off the x-axis. And of course, cosine squared, same deal. if you graphed its squiggle, it would also bounce up and down. It would just have a phase shift, so it might look like that. Except here's the thing. Negative cosine squared flips it. So it ends up being down here. And you end up, oops, that was the wrong one. So you just end up with the same graph underneath. Pretty sweet. All right, there's other times that you're going to need trig identities for sure. So for example, on this one, sine squared, cosine squared. Now we'll probably, later in calculus, we'll show you the power reducing formula. But basically, you can reduce the power of these things. Sine squared is, you know, it can reduce to sine of the first power of 2 theta or something. But the way easier way to do this is just realize, you know what, sine squared plus cosine squared is just 1. Integral of dx is x, add c to it, and you're all done. Pretty crazy, right? So those trig identities really come in handy. The ones you've got to know are that sine squared plus cosine squared equals 1. You got to know that cosine squared minus sine squared is cosine of 2 theta, or 2x. Whatever the letter is, just double it. And you got to know that the sine of 2 theta, or sine of 2x, equals 2 sine theta. Oops, we're doing x's. Sorry, I forgot. Sine x, cosine x. So this is called the double angle formulas. Cosine x equals this stuff, and sine 2x equals 2 sine x cosine x. So you can see this is the only way we can convert from like 2x's to single x's, or vice versa, is using these double angle formulas. All right, so once we got this, so we're just going to replace this with cosine 2x, and now we have something we can actually integrate. Because now it's just a simple u sub situation where u equals 2x. So du is going to equal 2 dx. And that means the integral cosine is sine 2x. Oops, so we forgot the 2 right here, which means a 1/2 out front. So it's going to be 1/2 sine of 2x plus c. All right. Identities, man, they're your friend. Last one, tangent squared. All right, what can we do with this? Well, I mentioned before that there's a trig. We use the secant squared and tangent squared show up in the same identity. Now I'll show you how to derive that identity. Sine squared plus, because I can't really remember it off the top of my head sometimes either. Sine squared plus cosine squared equals 1, right? Well, if we divide everything by, I want to get tangent, so we'll divide everything by cosine squared. And what that gives you is tangent of squared plus 1 equals secant squared of x. Now why is this so great? Well, tangent squared is not integratable, but I have an integration formula for secant squared, and I have an integration formula for 1. It's just a power rule. So I'm going to reorganize this so that tangent squared equals secant squared minus 1, and that's what I'm going to integrate instead of tangent squared. So I'm just going to replace tangent squared with secant squared x minus 1 dx. Alright, and that was super clever because secant squared is really simple. Secant squared x integrates to tangent of x, and negative 1 just integrates to negative x, and plus c, of course, and we're done. So trig identities, they're your friend. They help you out. Good stuff. And for a lot more trig formulas, a lot of classes, I'm not saying all classes, but a lot of classes will do something, they'll do just a lot of different powers of sine. So they'll have you integrate sine to the 4th x dx, and they'll have you integrate sine to the 5th. And it turns out, sine to the 5th power of x, it's just going to turn out there's a lot of different tricks you have to use for these higher powers of sine and cosine. So there's actually going to be probably a separate chapter about this later in calculus, because it's more of an obscure topic. All classes don't do it, so I don't want to hammer it right now. Right now I'm really focused on u sub, but in a later chapter we'll be doing powers of sine and cosine, and that's where we'll get into power reducing formulas, just all the different tricks you can use to deal with higher powers of sine and cosine. It's going to be similar to what we've just done, but it tends to be really plug and chuggy, and we'll learn just like four sort of sets of steps that work for every problem. So look forward to that if you really like integrating trig functions.